Hello, class. Today we are going to follow up with drawing our Lewis structures by using a technique called determining the formal charge. When I last saw you, we looked at CO2 as an example, and there were actually two correct ways to write the Lewis structure for CO2 based off of our rules that we put in place. What we're going to do is end up using formal charge to figure out which of those structures is actually the best one. So on some scratch paper, or if you have a whiteboard or wherever, go ahead and draw this molecule, SeO2. If you need to pause, do so now. Okay, so selenium has 6 valence electrons. And we know that oxygen also has 6 valence electrons, times the 2 oxygen that we have in our formula. We end up with a total of 18 electrons at our disposal. Now, this one is tricky because we want to look at our center atom carefully. Selenium is going to be the least electronegative, so we're going to make our skeleton between each of those 2 atoms. Now, out of that total, we've used 4, so now we have 14 electrons left over. As we did before, we start on the outside and work our way in, completing our octets for our oxygens. I've used 12 of my electrons, and I can put my last 2 there on the selenium in the middle. Now, I have some options here. I can take a pair and make a double bond here, or I could take a pair from the other side, oops, and make a double bond here. Both of those are valid structures, and we'll explore this idea of resonance later on to help us explain why that is. But there's also a third possibility. One of our possibilities involves us doing both of those things. So what we'll do is we'll take a pair from each side and we'll share them to make a double bond. Now, wait a minute. Something's weird here. I thought you said we can't have more than 8 electrons. Count up how many we have here. Indeed, we do have 10 electrons here. Now, here's the catch. In class, we might have discussed this. We haven't discussed it in our videos yet, but we are going to talk about how certain elements can have an expanded octet of electrons. We know that when we're talking about electron configurations, we've pretty much been limited to 8 electrons because we only have s and p orbitals for most of our things that we're showing the Lewis structures for. We know that the s orbital can have up to 2 electrons, and we can have up to 6 electrons in the p orbital. What ends up happening is that elements that are in the third row and below have extra electrons that it is believed participate in the structure or in the valence shell. So there's some theories on those electrons coming from the d orbital, but there's not a whole lot of proof at the moment as to whether or not those electrons are really actually participating. But we do have data that suggests that we can break the octet rule for some of those atoms that are in the third row and below. And it only works if those atoms are in the center. We'll talk about that a little bit more in another video, but this certainly is one of our options that we can possibly look at. So in total, we've got 3 options. We've got one where the double bond was formed on the left. We've got one where the double bond was formed on the right. Or we have this expanded octet where we end up with 2 sets of double bonds and a lone pair on the center. So what we're going to do is explore this idea of formal charge to figure out which of those is the best one. So the best Lewis structure has the least number of atoms with a formal charge, aka as many neutral atoms as possible. If the overall molecule has a charge, we know that formal charges will add up to the total charge. So let's say we're dealing with a polyatomic ion and it's got a charge of 2 minus. That means at least 2 of the atoms have to have a negative formal charge, and that it would add up to our minus 2. Typically, we only see formal charges of +1, -1, and 0, but sometimes you may see a +2 or a -2. What a formal charge essentially is a way that chemists can keep track of how many electrons something should have versus how many it ends up having in the structure. And we know that it's not an actual charge. It's not a charge like in the sense of a cation or an anion, but it is an uneven distribution of electrons. And that uneven distribution of electrons will matter later on when we look at things like polarity and intermolecular forces. So to calculate our formal charge, we have to determine the number of valence electrons that a particular atom should have normally, aka look it up on the periodic table. If I'm trying to figure out a formal charge of a particular carbon, I know that carbon has 4 valence electrons, and everything is going to be done in context of those 4 valence electrons. We're then going to count the number of non-bonded electrons, aka the number of dots, or the number of electrons taken up by lone pairs. And we're also going to count the number of bonds that an atom has. If it has a single bond, that counts as 1. If it has a double bond, that counts as 2. And if it has a triple bond, it counts as 3. We're going to subtract the number of bonds and the number of dots from the lone pairs from that valence electron number. And that will give us our charge. So here, I start with the valence electrons for each. We already looked at the valence electrons when we figured out our original total number of electrons. We had 6 valence for selenium and 6 valence for oxygen. I know that if I'm looking at selenium, selenium has 2 dots existing as a lone pair, so that's why I subtracted a 2. And then it's got a single bond and a double bond. So that is 3 lines in total, so I subtracted a 3. 6 minus 2 is 4. If I subtract another 3, 4 minus 3 gives me a positive 1. In this structure, the selenium has a positive 1 formal charge. So oxygen has 4 dots for the lone pairs here, so I subtracted 4. And it has 2 lines in the double bond, so I subtracted a 2. This ends up with a formal charge of 0. If I do the same process for the one on the right, there are 6 dots and 1 line. This ends up with a -1. If you were to do the same calculation for this structure, it looks like it's completely flipped, so you could probably guess that this is -1, this is +1, and this is 0. But then if we look here for this one, for selenium, I've got 6 as my valence electrons, I've got 2 dots, and I've got 4 lines. When I subtract that, I end up with a formal charge of 0. When I go through and do this for each oxygen, I notice that these oxygens look the same now. I've got 6 valence electrons, minus 4 dots, minus 2 lines. And I end up with a 0 formal charge for those as well. Guess what? This ends up being, even though it looks strange, the best possible structure for this molecule because I have reduced the formal charges.